So let's continue with our EIGRP distance vector routing protocol. First of all, we have already introduced the working principle of our distance vector routing protocol. Next, we will talk about some features and technical points of the EIGRP distance vector routing protocol. First, let's introduce our EIGRP. In the EIGRP distance vector routing protocol, it introduces 3 tables. The first table is called the neighbor table. In fact, in the predecessor of our EIGRP, our distance vector routing protocol, some of you might not have gone through it. Some might have just entered NP directly, and some have gone through NA before entering NP. The REP protocol does not have a neighbor table. Let's briefly talk about how the REP protocol works. As usual, in the distance vector routing protocol, each router has its own database. Let's take R1 and R2 as examples. Suppose R1 puts its directly connected route, 0 interface directly connected route into the database, 172.116.12.0-24, associated interface 0. R1 puts its directly connected route, 10.10. 1.0-24, associated with our loopback 0 into our database. For the distance vector routing protocol, suppose it is REP. For the REP protocol, it updates in a periodic manner. Periodic updates every 30 seconds. As long as our 0 interface runs the REP protocol, every 30 seconds, I will tell R2 my routing entries. Every 30 seconds, as long as my 0 interface runs REP, I will tell my routing entries every 30 seconds. I will tell my neighbor my REP database entries. What if I don't want this route? Suppose my interface does not run the REP distance vector routing protocol. I don't want your routing entries at all. But it's useless, right? Useless. As long as I run it, I don't care 3,721. I don't care if you want it or not. I don't care if you want this route. I'll throw it all at you. Just throw it, right? You have to take it even if you don't want it, right? Of course, for R2, these database entries, I discard them all, but isn't this very insecure, right? You think, the other party doesn't need this route. You announce the route to him, is it? Can it be like this? Definitely not, right? What do you have to do? Just like what? Just like unrequited love, right? You keep pursuing them, right? But you haven't experienced them. You haven't felt their feelings for you, right? You just keep imposing your will on the other party. It definitely won't work, right? What we advocate is a process of mutual affection. So in our EIGRP, on the one hand, it's about security. On the other hand, it's about identifying our announcements. Found it, just to let you know, the current CCIE Lab exam requires Python. This student has a Python problem, I told him, because he is about to take the exam. He is really anxious, so I made an exception today. I won't do this in the future. Because he is about to take the exam, I just give him a little special care, I told him. Human touch, right? Yes, there is a bit of human touch in Python's dictionary. Except for the last line of content, each line of the other content in the dictionary list, except for the last line, each line needs to end with a comma. Just this once, help him debug. He is about to take the exam. The code part. This code is very simple. This Python code is very simple. In the previous version of the lab, our code only had a total of 7 command lines, 7 statements. This Python exam question. It's not difficult. There aren't many command lines. It's very easy. Why do we say this version is the hardest in 20 years? Because each question he asks is not difficult, right? I'll take a pill. I still have a cough. In our distance vector routing protocol EIGRP, it has a requirement: we must become neighbors with each other. In EIGRP, our devices must establish neighbor relationships. After establishing a neighbor relationship, they will exchange database items with each other. We won't be like before. I will impose on whether the other side is willing to accept my topic or not. I will announce every 30 minutes. In our EIGRP, we must establish a stable neighbor relationship. After establishing a good neighbor relationship, then I will announce the news to you. I will announce the news. So how to establish our neighbor relationship? This involves a feature of our EIGRP. In EIGRP, first, we need to recognize a packet. It's the EIGRP packet type. First, we need to recognize the hello packet in our EIGRP, once our interface between the two runs EIGRP. It first needs to send out a hello, send a hello packet. Who is the source address of this hello packet? Who is the destination address? Let's not talk about it for now. Let's first understand the hello packet. For example, R1's 010 interface. I run EIGRP, I send hello, send it to the link, send to the link. So R2 can receive. If we talk about R2, then what am I doing? Sending hello packets. I also ran EIGRP. It's like students. Suppose today you are a resident of the community. Then your next door moved in a new neighbor. He came to your house to visit you with fruits and gifts. Then we interact with each other, right? I greet you, you greet me. What do we do with each other? We get to know each other. We met, then we verified each other. For example, we verified our characters after meeting. I think the opposite side is very polite, right? Then I also give him, that is, he is polite to me, I am also polite to him. Then both people are very harmonious. What do? We can establish a neighbor relationship. In EIGRP, we send hello packets. Just do the interface once. EIGRP will send hello packets. Then, after receiving the hello packet from the other party, after we get to know each other, we can establish a neighbor relationship. Of course, we certainly need to verify some content. Can't say a stranger, I immediately make him my neighbor. Definitely need to educate some content. This involves what we will talk about in the next issue, a condition for establishing a neighbor relationship. We won't talk about it here. Let's first understand the hello packet. Once the EIGRP interface runs, should say once the router interface runs, EIGRP, then it will start sending immediately. Then, by default every 5 seconds, time to send hello packets. Then, after exchanging hello packets with each other, if the teaching content is correct, if the check is correct, teaching is correct. Then a neighbor relationship can be established. This is our EIGRP hello packet. What else does it involve? This is the first function of our EIGRP. Then discover neighbors. It has other functions. We will talk about it later. Good students. The first function of EIGRP, the first function of the hello packet is to discover neighbors. Then next we come to this environment. Let's see how EIGRP establishes a neighbor relationship. How do we run EIGRP with the 2 points we just learned? A neighbor table, a hello packet. Let's establish an EIGRP neighbor relationship in the network. Then the router has already started, 3 routers. We configure it simply. First enable configure terminal. We configure the device name. Host name is R1. We initialize line console 0 exec timeout 0 login sequences. Then in this way, it won't operate for a long time. Kick us to the screen after program. When a log message appears, can automatically change lines. This is the function of our command line. Initialize the command line. R1 here. The same host name is R2, line console 0 exec timeout 0 login sequences. Then there is R3, host name is R3, then R3, line console 0 exec timeout 0 login sequences. All right, then initialization is complete. 3 routers. Next, we configure the addresses of the 3 routers. R1's 0.0, no shutdown. Start it. IP address is 172.16.12.1, The automatic mask is high 24. Root back 0. We create a logical interface. This loopback interface. It is a virtual interface, so it's used for testing, used for some virtual purposes. Let's do the test. IP address, January 1st 10. Circle it. Configure the IP address. Interface 0.0 on the R2 side. No shutdown. The IP address is 172.16.12.2, 24-bit mask. Configured 0.1 interface. No shutdown. The IP address is 192.168.23.2, 24-bit mask configured. On the R3 side, 0.1 interface. No shutdown. The IP address is 192.168.23.3, 24-bit mask. Look at this diagram. 192.168.23.0, 24 subnet. Our host bit is 0.3. 0.3, 24-bit mask. And our loopback 0 interface. IP address 10.10.3.3, 24-bit mask. After the configuration is complete, we can check first, show IP interface brief, see if the address is configured, whether the interface is turned on, R2, show IP interface brief, see if there are any problems, R3, show IP interface brief, see if there are any problems, check it. The second thing, see if we have a direct route, check the direct route, no problem, on R2. Direct route, so 2 direct routes, and R3, show IP route, 2 direct routes, open, direct route 2, both have direct routes. So students, in operation, running a dynamic router, it's the same in your work. I hope you can develop this habit in any of your experiments, in any of your projects. So at the beginning of the network deployment, when the address is configured, when preparing to apply the protocol, so you can pre-test this direct connection. R1, let's ping 172.16.12.2, comma. See if R1 and R2 can visit each other. No problem, R3, let's test it, ping 192.168.2.3.2, comma. See if there are any problems. So this approach can avoid the difficulty of troubleshooting in the future. You test it in advance. If you accidentally configure it wrong in the future, there is a problem. You can rule out the problem of this direct link, otherwise you will find out later. Why didn't it start? Why don't I have a route? You have to check it. It's more troublesome. So there is no problem with the connection. The addresses are all matched. Let's run the distance recognition routing protocol, EIGRP. So first, on Cisco devices, when we run the dynamic routing protocol, so it's nothing more than 3 steps. The first step, create. So the dynamic routing protocol, so how just frame or call the process. The first step is to create it. Some of the processes on Cisco devices, then all dynamic routing protocols. Of course, after learning IPv6 in the future, there are a few special cases. Then they all start with router. Router starts, for example, in the routing protocol. I want to run the EIGRP protocol. Then it's router, put a question mark. You can see that you can choose to run the EIGRP protocol. For example, router EIGRP. What you need to pay attention to later is, when creating the EIGRP process, you need to follow a number. What is it called? Autonomous system number. So you run EIGRP, you must set it. Such an autonomous system number. Of course, we will talk about it later. If we want to run IPv6 EIGRP, or we want to run multi-protocol EIGRP, we must still do what? For example, use a name to indicate our EIGRP process. But inside, we still have to specify this AS number. You can't escape it. You must do this AS number. So the AS number, I mentioned it before, it is used to indicate such a group of devices, a collection of devices. So simply put, we need to explain R1. Which community do I live in? R2. I also live in which community? Then you think, our subsequent relationship between R1 and R2. What relationship do we want to establish? Neighbor relationship. What is a neighbor? You are in the same building. Then you can become neighbors between left and right. You can become neighbors up and down. But you say you live in a building in Shanghai. He lives in a building in Beijing. Can you two become neighbors? No, right? What is a neighbor? At least we have to do what? Inside a building. Then between you two, for example, adjacent up, down, left, and right. 2 or 3 gaps are almost the same. You can't say you're so far away. You become a neighbor. So what does this AS number judge? We said it is a collection of devices. A collection of devices. So if we want to become neighbors, we have to live in the same community, in the same building. Suppose we create an EIGRP 90 AS number. This is the X value. Then XS is the AS number. Then 2 EIGRP routers need to ensure the AS number is consistent. To establish an EIGRP neighbor relationship. That's right, EIGRP is a distance vector routing protocol. BGP is called a path vector routing protocol. Then in fact, BGP, that's right. In terms of BGP, it is called path vector, called Advanced Distance Vector Routing Protocol. It has already left the category of distance vector routing protocol. It's a path vector routing protocol. Need to distinguish. Then EIGRP is an IGP protocol. It cannot operate between our AS and AS. You need to pay attention to this place. This A's number is specifically for then we two are in the same AS, we are devices in the same community, then we can establish an EIGRP neighbor relationship between us. You have to live in the same building, the same community, the same room, inside the same house. You can become a neighbor. You can't say one lives in AS 65,535, one lives in AS 65,534, you live in Beijing, one lives in Hong Kong. Can you become a neighbor? That's definitely not possible. Becoming a neighbor has conditions. Then the AS number must be consistent. For example, on my R1 side now, my router EIGRP has a 90. Write anyone. Then the first step is to create a process. If the second step is to run EIGRP, what we must pay attention to is you must activate the interface. Before learning BGP for dynamic routing protocols, what we must be clear about is activate the interface, let the interface's support route go into the database. For example, link status, activate interface. Put the link status information of the interface into the database. The second action must be to activate the interface. So how to activate it? A special command line called network. Then the network command has two functions. Then the first function, the interface address matched by the subsequent network segment of the network, the direct connection corresponding to this interface, the interface corresponding to this address. Run the dynamic routing protocol. Second, the interface address matched by the subsequent network segment of the network, the direct route of the interface corresponding to this address. Stored in the EIGRP database. In EIGRP, we use the network command line to activate the interface, make it run the dynamic routing protocol. And through the network command line, put our direct route corresponding to the interface into our database. So if it's on RE, we have already created the EIGRP process. I need to let my R1's 0, one interface run EIGRP. So for the sake of certification, I'll capture a packet here. Just created our EIGRP framework. So actually, EIGRP has not been run yet. So in the packet, we can only see the second layer protocol. This place has no use. A session protocol sent to itself, it's useless. There is no EIGRP related information. Our interface is not running the dynamic routing protocol, EIGRP. So use the network command line. Its function is to activate the interface. So how to activate it? Find a network segment. There are 3 schemes to activate the interface in EIGRP. The first scheme, our network command line matches a network segment. This network segment matches the interface address of our router, for example, the interface address of R1, 172.16.12.1, comma. This is our R1's interface, IPv4 address, so it belongs to 172.16.12.0-24, comma. An IPv4 address and such a network segment. So this network segment includes 172.16.12.1 to 172.16.12.24, comma. These host addresses. So our first scheme to run EIGRP, called positive mask declaration. Very simple. By using the network command line, then match the network number of the subnet to which the interface belongs, and the normal subnet mask. So make the network command line match such a network number, and subnet mask match such a network segment, the interface address on our device matched by the network segment. Let the interface run. EIGRP, for example, come to R1. Our interface brave 172.16.12.1, comma. Belongs to the 2.0-24 network segment. I directly network 172.16.12.0, comma. Then the positive mask belongs to 2.5.25.25.0, comma. Match a network segment through the network command line. This network segment 172.16.12.0-24, includes IPv4 addresses from 172.16.12.1 to 254. So on the R1 router, we have an interface address 172.16.12.1, matched by the network segment. We matched an interface address, the address of the 020 interface. What to do after being matched? Our interface. The interface corresponding to our address, the 020 interface corresponding to our address, can run our EIGRP. Classmates match the interface address. The corresponding interface runs EIGRP. Go ahead, look at the packet. So immediately you see the first packet came out. We saw an EIGRP hello packet. Students a hello, this hello packet. Source IP address is the interface address where we run EIGRP hello packet. Source address is the interface address running EIGRP. So the destination IP address is our EIGRP multicast IP address. That is 224.0.0.10. So how do we receive this multicast packet? What is this multicast? Let's briefly mention it, because it may have been a long time for our NA students. Let's listen. So in the network, the common packet types we see, there are three: unicast, broadcast, and multicast. For example, host A, B, C, D, 4 hosts. We are in the network segment 192.168, 1.0-24, the host ID is just 192.168.1.1, B is 2, C is 3, D is 4. Suppose now we want to unicast. Unicast. What does unicast mean? 1-to-1. I send a message to another person. For example, now 192.168.1.1. So I send a packet to 192.168.1.2. I send you a message. This is unicast. Second, what is broadcast? What does broadcast mean? It's called one-to-many. How to do one-to-many. So suppose all our addresses, what are we all in the network segment? 192.168, 1.0-24, So in this network segment, we said, when all host bits are 1, the first 24B and the last 8B host bits. When all host bits are 1, this address 192.168.1.255. So this is the broadcast address in our subnet. When I, for example, host A 192.168.1.1, I send a message then to 192.168.1.255. So I, for example, according to this diagram R1, at this moment, I want to visit 172.16.12.255, this each destination address. Look at what? Look at the routing table. Access destination address. Ping 172.16.12.255, Okay, is there a route that can match the destination address? There is a direct route. Teacher, isn't this a broadcast address? The broadcast address is not an address. The destination address can be matched by the direct route. Forward, according to this direct route, R1 will directly encapsulate the packet. Source IP address. The initial interface is the source address. The destination address is the broadcast address of our network segment. The outgoing packet, so the broadcast packet. Any host in our network segment can all receive this broadcast data flow. Then, what to do after receiving the broadcast packet? Can respond, IB can reply, C can reply, D can reply. So you find that when we ping this packet, for example, repeat 20 packets, so its reply is different from our normal ping packet. How does the normal ping packet reply? 5 exclamation marks, isn't it? But now, when we ping this packet, stuck, what's the situation? Look, his side is not like our normal ping unicast packets, exclamation mark. Instead, what is it? Who replied to our message and when? Because of this packet, all hosts in our entire network segment can receive it. When they reply, we will have a message display here. Who replied to me? This is a one-to-many broadcast. So what is multicast? Multicast multicast is also one-to-many, but we can do many-to-one, can do one-to-many, can do many-to-few. This multicast of ours is called multicast, can also do one-to-many, but we changed the word of broadcast. What is the one-to-many of broadcast called? It's called one-to-all. Distinguish it from our multicast in this way. Multicast is one-to-many, broadcast is one-to-all, understood. So if it's such a requirement, the main suggestion is, I only want to send messages to host B and host D, then I don't want to send messages to host C. That's simple. Teacher, you send a unicast to host B. You send a unicast to host D. Isn't that the end of it? Sending 2 unicasts can solve this problem. Don't send to C. Think about it. If there are many devices in a network, I have 254 devices. I only want to send data traffic to 252 of them. Do I have to send 252 unicast packets? Repeated encapsulation packets. Repeated forwarding, it's a waste of resources. So what does multicast mean? When we talk about IPv4 address classification, Class A, Class B, Class C, Class D, 1 to 126 is Class A, 128 to 191 is Class B, 192 to 223 is Class C. And we've talked about Class D addresses. The first 4 bits are fixed at 1110. It represents the range from all IPv4 addresses starting with 224 to those starting with 239. That is to say, from 224.0.0.1 to 239.255.255.255, comma. All are multicast IPv4 addresses. So these addresses can let us use them in multicast. So why do students understand this multicast? Like a WeChat group. So B joins a multicast group address. For example, 239.1.1.1, D joins a WeChat group, 239.1.1.1. Then next, suppose our host A, my dedicated 192.168.1.1. So this time, the destination address I send is a multicast address of 239.1.1.1. Students, then only members who have joined this group. You're in this group chat, you've joined this group. You can unpack this data traffic, see the message inside, and those who are not in the group. Even if they receive the package, I can't see this data traffic. This is multicast, students. So only those who have joined the corresponding group can see the message, so now let's reflect it in our EIGRP. Wait a little bit. Damn, in EIGRP, our multicast address is 224.0.0.10. So once our interface runs EIGRP, our 0 interface runs EIGRP, what will happen then? Show IP interface 0. What do you see? Look at our 0 interface's network layer. IPv4 address information. What do you see? Our interface has joined the multicast group. Address 224.0.0.10. So students, once our interface runs EIGRP, we will send hello packets to 224.0.0.10, which is the multicast address of EIGRP. So for this interface on the opposite side, only such an interface. It also runs EIGRP. It will join the 224.0.0.10 multicast group. It can also receive my hello packet and check the information inside. So students, what do we have now? Both sides of the router are running EIGRP, can send hello packets, can receive each other's hello packets, can establish an EIGRP neighbor relationship. So we find that in the network now, only R1 is continuously sending EIGRP hello packets every 5 seconds. Understand, we have only activated the 0.20 interface of R1. By the method of positive mask, directly declare the network segment to which the interface address belongs, network number plus positive mask, then declare that the interface is running EIGRP. Having said that, after the interface runs EIGRP, our corresponding direct route of the interface can be put into the EIGRP database. Now let's go back to R1 and see Show IP-AGRP topology. Our EIGRP database table is called the topology table. Of course, this is a name. Then EIGRPs, sorry, a bit here. The second table is called the topology table, also known as the database table. Then what is stored is our EIGRPs. This is the database table, just the name is called the topology table. Stored the EIGRP database entries. Then press enter to see, look at our EIGRP 90, our direct route. Connected direct route, key interface 0, 0 direct route, 172.16.12.0-24, comma, stored in our EIGRP database. But what else is there behind? Successor FD. What is this? We'll talk about it later. We haven't talked about the DUA algorithm yet, how to do fast convergence. Haven't talked about it yet. How to calculate the metric. Haven't talked about it yet. Don't worry. We have put the direct route in. Then let's look at the back. If our R1 database 0 interface, our interface belongs to 10.10, 1.0-24, comma. Such a subnet, then I can go to router EIGRP 90. In the process, activate the network interface, match the network segment of our loopback 01 interface, 25.25.25.0, comma. Includes the host address, 10.10, 1.1-24, comma. Our 10.10.1.1 matched interface, matched address, corresponding interface. Sorry here, matched interface address. Our corresponding interface runs our EIGRP, and the direct route is put into the database. Show IP EIGRP topology. Look, it's in. Put the corresponding direct route into the database. This is our EIGRP's work. Then what do we look at next? Since we have run our EIGRP, but now we haven't established an EIGRP neighbor relationship yet. Let's look at the configuration first. Just now we said that we activate our interface to run EIGRP through the positive mask method. Let's show running config now, our configuration in EIGRP. Then for the network command of EIGRP, you find we activate our interface through the positive mask method, 255.255.255.0, comma, to run our EIGRP. But what has it become in the configuration command line? This thing is called inverse mask. Then the inverse mask is very simple. Inverse of the mask. Turn our original to 55.255.255.0, comma. Turn our original 255.255.255.0, comma. Turn our original positive mask. Our original 255.255.255.0, comma. Our original 255.255.255.0, comma. Our original subnet mask. Inversion, what is it called? It's called 1 turns into 0. 0 turns into 1. It's called 0.0.0.255. It's called inverse mask. But in fact, in our Cisco, we prefer to call it a wildcard. So you should have heard about wildcards in NA. If you haven't taken the NA class, it's okay to come to the NP class today. You don't have to understand what a wildcard is. Just think of it as an inverse mask. Understood? Students, just think of it as an inverse mask. So we see when we declare an interface using a regular mask. When declaring a website, it automatically becomes an inverse mask. So in fact, our regular mask declaration, it's just a roundabout way to activate our interface, to run our EIGRP. For example, network, for example, 172.16.12.025.25, 25.0. So the regular mask declaration, so it can successfully declare the interface address belonging to the regular mask, right? Regular mask declaration, but then the device will automatically convert it to an inverse mask in the configuration. So next we're going to talk about, in fact, we have found, actually, the inverse mask is the normal operation of our EIGRP declaration, inverse mask declaration. So why is that? Students who have learned about wildcards in NA can understand very well. But we're not going to talk about wildcards today, because some students may not have taken the NA class, right? Let's just talk about inverse mask declaration. So it's through the network command line, matching the network number of the subnet to which the interface address belongs, and the inverted subnet mask to match. Sorry, not to match, it's already written here. To match, don't need to preface it. Suppose it's on R2. So on R2, I want to activate my interface, activate it, using the inverse mask. Router EIGRP first step is to create a process. The second step is to activate the interface with the network command line. So R2's 0, 0 interface 0, 0. So its address is 172.16.1.2.2. Belongs to the 172.16.12.0-24 subnet, regular mask 25.25.25.0. So the regular way to declare an inverse mask, we go to 172.16.12.0. Regular mask 25.25.25.0. We invert it, 1 turns into 0, 0 turns into 1. 0.0.0.255, activate our interface, run EIGRP. So you see, the neighbor comes up right away. Why? Because R1 has been sending EIGRP hello packets tirelessly. But R2 hasn't run EIGRP. I haven't joined the multicast group 224.0.0.10. I won't receive your hello packets. Now I'm running it too, I can receive it. So I can receive your hello packets. And I also send you hello packets. They recognize each other. Once recognized, we establish an EIGRP neighbor relationship. Okay, students. So let's look at R2's 0. 1. We can also activate it 192.168.23.0, regular mask 25.25.25.0, right inverse 0.0.0.0.255. But what needs to be noted is show running config. If our inverse mask and the main class of our interface address are the same. What main class? For example, R2's interface address is a 192 prefix address. This is a Class C address. So for a Class C address, the original 192.168.23.0 is the first 24 bits for network bits. The first 24 bits of Class C address are the network bits. So when you declare now, it is also what? 0.0.0.255, invert the mask. The first 24 bits are network bits. It is the same as our main class. So why? It will hide the command line. 0.0.0.255 is invisible because of your declaration. It is the same as the main class of our interface address. Why should I display the same? It will not be displayed. Students, why was 172.16.12.1 before we invert it? When writing as an inverted mask, why did it show up? Because our 172.16.12.1. What is 172 starting with Class B address? So its main class is 172.16.0.0. Different. So it is fully displayed. So students. Of course, this is a display issue. Actually, when we usually declare, it is imperceptible. So you just need to pay attention to these details. So on the R2 side, we also activated 2 interfaces to run EIGRP. Let's go to R2's 0. 1 interface to capture a packet. We should also be able to see R2 is constantly sending EIGRP hello packets. To R3. Buy a packet. Here comes the EIGRP hello packet. R2 sends packets to the multicast address. So let's go to R3 similarly. We have the third declaration scheme. The third declaration scheme. So this third declaration scheme, it is precise declaration. So through the network command match the interface address and set. So for example, the positive mask is minus 32 bits, 25.25.25.25, or the inverted mask of minus 32 bits. 1 becomes 0, 0 becomes 1, right? All becomes 0, 0.0.0.0. So we match our interface address through the NATO revolution bar, for example, on R3 router EIGRP 90. Our interface address is 192.168.23.3. I'm too lazy to calculate the mask. Don't want to calculate, right? So what do? Directly network. My interface address, 192.168.23.3. So the positive mask is 25.25.25.25. Let's see if it's 192.168.23.3-3-2. All bits are network bits, fixed. In this network segment of ours, there is only one address. It is 192.168.23.3. The interface address, matched by the network segment. Our interface address is 23.3. Matched, right? Is it matched? There is only one address inside, just match 23.3. What to do after matching? 011 interface runs EIGRP, isn't it, students? Go you. Okay, now look at the configuration show running config. Look, our neighbor has been washed. Actually, it proves that it's already good, it's already running. 0 is already running. So EIGRP IP, look. Here, it will automatically convert to inverted mask, become 0.0.0.0.0. So of course, when we declare, of course, you can also directly declare the inverted mask. For example, let my loopback 0 interface 10.10.3.3. So network 10.10. 3.3 precisely matches positive mask 4.255, inverted mask 0.0.0.0. So it only includes one host address, just at 10.10.3.3. The matched address runs our EIGRP only, E10.10.3.3. The matched address runs our EIGRP. The matched address runs our EIGRP, so R3 has a signal to run. Students, so this is our EIGRP running active interface. Let it run EIGRP, and put the corresponding professional route into the database scheme. So each has its own advantages. So if you are using a positive mask, or if it is a reverse mask declaration, its role is very clear. How clear is it, for example? There is such a router. So we have two interfaces. One interface address is 192.168.1.0, 24, like 1.1. Another interface address is 192.168.2.1. 24. So if we say on this router, we go to network, what can we do? Take a larger range. For example, 192.168. If we declare exactly 192.16, that is minus 32 bits. So only this interface address can be declared. The corresponding interface runs EIGRP. So if there are others on our device, for example, the same network address, so it will not be declared. It's very precise. Especially, please declare this address. The corresponding interface runs EIGRP. I'll talk about this range. First, for example, we declare 192.168.0.0. 16. We network 192.168.0.255.255.0.0. So a network segment contains the host address from 192.168. So start with 1.1. Start with 0.1. All the way to 190 to 2.168. So 0.255.255. So on router R1, these two addresses can be included in this network. So using such a command line can activate my two interfaces. Both run EIGRP. But if we limit, we use precise declaration. If the declaration is a network segment, so both interfaces can run. So if it's more precise, I network. I declare 192.168.1.0, 24.255.255.255.0. So only 192.168.1.1 is matched to 192.168, so 0.1.255. So these addresses are all matched. Then run our EIGRP. But if we have a special situation, suppose we have this situation now. The left side is 192. 168.1. Let me calculate 1.1-30. The right side is 192.168.1.128, for example, minus 30. So if we go to network now, 192.168.1.0. So it includes addresses 1.1-255. Both interfaces will run. But what if I use precise declaration? So I just go to network 192.168.1.132. Only includes such an address. Right, even if we are under the same subnet, 192.168.1.0. 24. But this only matches the address 192.168.1.1 only. This address interface will run EIGRP. So this is the most precise way. The most precise way to match exactly. The only one address corresponding interface run dynamic routing protocol. So if you ask me which plan I prefer, I say what I like is precise declaration. This is my personal hobby. Of course, during the exam, so our solution is through the reaction code. Students, of course, I personally prefer precise declaration because it's stable. I won't declare the wrong interface into EIGRP how to say it. Actually, there are pros and cons. If you have one on this device, for example, this is a switch, right? You are all 3 ports, so you might have about 20 interfaces to run EIGRP. Then you definitely want to find a way to omit, right? Of course, if you match precisely, typing more than 20 times is also possible, right? We all do it according to the situation. Any questions? What do you think the problem is? If it's a precise declaration, then, for example, under the R3 router, it's the same network segment I have connected other devices. Why is it useful? For example, I have connected one on the R3 side. I have an address here. My address is 192.168.1.1. 24. So I might have connected a 192.168.1.0. 24 host on the other side. I understand what you mean. So I declare precisely. What you need to pay attention to is, what is my precise declaration for? It's to activate the interface. It's to activate the interface. I am trying to get this interface to run EIGRP. So what is ultimately put into our database? It's the directly connected route corresponding to the interface. Do you understand what is ultimately put into the database? It's 192.168.1.0. 24. It's not something like 192.168.1-32. That thing is when we declare, in order to precisely reach my unique interface to run EIGRP. So after the interface runs the protocol, what is put into the database is its route, students. So what is transmitted out is also the route in the database. So what will we receive at our time? What we receive is such a network segment route entry. Go through R3. We can still do what with the host below access out. What you must pay attention to is the function of the network password. It's to activate the interface. Precise declaration. And website are both multicast, yes, that's right. Because if it's this host address, 192.168.192.168, for example, 1.4. So our R3 interface runs EIGRP. This route is passed to our R2. So R2 knows the network segment, 192.168.1.0. 24. I will go through who go through R3. I can access 1.4. Of course, it can be sent according to the routing standard assigned to R3. You must not confuse the network segment we use for declaration with the network segment we transmit for routing. The function of our declaration is very simple. It's just to activate our interface, the function of the network password, before you learn BGP. There is only one: activate the interface. Activate our interface to run the mainland protocol. Then what is put into the database? Actually, it's our directly connected route corresponding to the interface. Do you understand? Any other questions? Zheng said that precise declaration and segment declaration are both multicast. Yes, by default. Your precise declaration and segment declaration are both to activate the interface. When the interface runs EIGRP, what does it do by default? Join the multicast 24.0.0.10 send hello packets to the multicast. Any other questions, students? Teacher, can I ask a question? Go ahead. These methods are all to activate the interface, yes, but I don't seem to understand it very well. Why? Why go around, right? To activate that interface, why do you have to declare it, right? Because in fact, this is how it is designed. Later, when we learn OSPF, we also found out, since I am to activate my interface, to run the dynamic routing protocol, why do I have to declare a network segment through the network command line to go around? So in the later OSPF, we have the fourth activation method called interface activation. This is what we will learn in OSPF later. We directly enter a certain interface. For example, interface, I want to run my zero interface dynamic routing protocol OSPF. Then I will just do OSPF one area, 0. Let's just do it under the interface. Let our interface run such a dynamic routing protocol. No need to find a network segment. Why has the default become a 24-bit mask? Not default to 16 bits. For example, the 192.8.2.0 network segment is also available, because when we declare it, right, even though you see if we are on the R2 side, we go to network, a larger network segment, like 172.16.0.0, 16. Can you say, let our interface run EIGRP? It can, but teacher, why do you say that you must declare a positive mask? Try to declare our interface mask. Because we have talked about such a network segment, it was also demonstrated above and below just now, because its range is relatively large. Suppose I have an interface on R2 that is 172.16.3.0. Such a network segment, won't it also be matched in? Then you declare that the range of this network segment is relatively large. It is very likely to declare other interfaces on our router. Also declared into EIGRP, but I don't want it to run. So in work, what do we often do? Involves a problem. It's a problem with a deployment plan. Try to be as accurate as possible. Don't hurt other ports. I just want my port to run. Then I'd better go in and declare, I don't mean that. Don't you mean that? You say, for example, you declare accurately on the R3 side. You declare a 192.168.1.1 of 32 bits accurately. You declared accurately. Then you just said, then if I connect a 1.2 below. You said it can pass, right? You say originally there is 1.2 can pass. Because why? Because your network, such a 192.168.1.1, 32 on R3. My network is to let my interface matched by this network segment. Let the interface run our EIGRP. It's for activating the interface to use. So after activating the interface actually puts in its direct route. It's 1.0-24. I hesitate here. I don't understand here. Why does it default your route to 24 bits? Why our interface address is 24 bits? Our interface address is 24 bits. Our interface corresponds to the direct route. It's how many bits your interface address is. It's for us. We put it in the database. Is our direct route. My interface's direct route. For example, on R1, we just saw it. So I let my 172.16.12.1. This interface runs EIGRP. So what is put into the database? What is put into my database? It's my R1's 0. 0 interface, its direct route. What is this? My 0 interface generates a direct route. Put it into our EIGRP inside the database. Understand or not, if my IP address, it's just a 16-bit, then the declaration is put into the database. Yes, it's also 16 bits. It's the direct route put in, understood. Thank you, teacher. Are there any other questions? Any more questions? If there are no questions, let's continue. It's okay to ask if you have any questions. It's my turn. It's okay, even if it's slower this round. We can talk more carefully, it's okay. You can ask if you have any questions, just like the student just now. You can ask any questions. Let's continue. But in EIGRP, there is no planned declaration. There is no such thing. We all declare through the network segment. Initially, they thought, because actually, students, why plan interfaces through network segments? This is what we have in REAP. It's our earliest design. This specific use in routing protocols leaves a drawback. One is an old flaw. Not to say it's a flaw. I can only say it's a bad habit. Because at that time, it was the main class, students. At that time, we were all the main class. In order for my interface to run, we can only declare through the main class. So in EIGRP, we have all retained bad habits. We still go through because before, it was all classified according to the class. Who would have thought classified by mask? There are some deficiencies in the design, so EIGRP, after all, also specifically uses routing protocols referencing such a pioneering design. So although the result has improved, many shortcomings of REAP changed a lot. But this declaration still has some problems. But later on, you see OSPF has reflected on it. Who can be so troublesome? Directly enter the interface declaration. Isn't it over, students? After all, EIGRP has been around for so many years. Continue. Just now, we talked about the declaration. Now our entire network is running the EIGRP protocol. Okay, then R3. For example, R1, start with R1. It will put its direct routes. Put the interface's direct routes into the database, 172.16.12.0 and 10.10.1.0. Students need to pay attention. Isn't it about exchanging database entries? Will R1 put its own 172.16.12.0 direct route announced to R2? Any students want to answer? Forget it. I want to answer. I think this one, 72.16.12.0 direct route. Will this database's direct route, will it be told to R2? Will it, kid? You ask the students at the back. You definitely know. You know it's him, will it? Will it? Yes, if not. Why is it called a routing protocol? Pay attention to a point. Students, think about it. We want to announce our interfaces 172.16.12.0-24, this direct route, to another, connected to 172.16.12.0-24, this network end of the router. Do you think it's necessary? Isn't R2 also connected to this network end? Doesn't he also have 172.16.12.0? Doesn't he also have R1 has 172.16.12.0? I am a direct route. You say R2 won't have it. He's also connected to the network point. We are establishing a neighbor relationship. He's also connected to 172.16.12.0-24. This network end. Do we need to repeat this? Network segments, route entry to R2. No need, he has it, students. So first, remember our announcement. The first point of the route entry. Then the router. It will not take the directly connected route of its own interface to write this. Router running, EIGRP, will not its own interface in the database. The directly connected route of its own interface from itself, from the current interface. Will not take the directly connected route of the current interface. From this interface, announce out. Because it's very simple. R1's database contains 172.16.12.0 R2's 0. 0 interface also belongs to 172.16.12.0. Also belongs to 172.16.12.0. It will also put its directly connected route into the database. So R1 will not take its own directly connected route generated by the interface. Announce it to the same network segment. Do you understand? My interface is in the R24 network segment of 172.16.12.0. I will not announce the directly connected route of my own interface. from this network segment again. Isn't this a repetitive announcement? There will be one on the other side itself. You give him another announcement. How can this work, right? Except for the directly connected route of its own interface, we will announce all other routes. So in R1's database, at first glance, there are two routes, but in fact, I will not throw the directly connected route of the zero. Zero interface from the zero. Zero interface. This is an invalid practice. What are we announcing non-directly connected? Routes other than our zero. Zero interface directly connected route. R1 will announce is the directly connected route of its own loopback zero interface. I will tell this database entry to R2, then come to R2, show IP EIGRP topology. What comes into our view? First of all, we will put our own interface, the corresponding directly connected route into the database, and I will not promote it from this. We will not announce the directly connected route of our own interface. From our own interface, then we can receive R1, telling us, look at 172.16.12.1. He told me. He has a 10.10.1.0, 24 route entry. He told me he has a 10.10.1.0, 24 route. So where did I learn from? I received it from my zero. Tisao zero interface 172.16.12.1 told me he has a 10.10.1.0.0 24 route. Then what to do? Calculate into route entries. Submit to our routing table A10.10.1.0. Appeared in the routing table I received from the zero interface. Then I turn around. What should I do when I need to access 10.1.0.1.0? Throw it out from my zero interface. Here, the entry I received from the zero interface. The other party told me he has a route. Then, when I go to visit the other party, of course, throw it back from the zero interface. So here involves two directions. So the first direction is called the direction of route transmission. For example, R1. So the direction of route transmission is like this for 10.10.1.0 in the distance. Vector routing protocol. Two directions specifically refer to the distance vector routing protocol. One direction is called the direction of the route note. It refers to the distance vector routing protocol, the direction of route transmission. R1 tells the route to R2. R2 tells the route to R3. This is the direction of route transmission. What about the reverse? The reverse is the direction of data traffic. Why? Because R2. We learn the route from R1. I know R1 told me it has a 10.10.1.0, 24 route. When R2 wants to access 10.1.0.1.0 in the future, the data flow goes through R1. When R2 announces this route to R3, R3 knows the 10.1.1.0, 24 route that R2 told me. When R3 wants to access 10.1.0.1.0 in the future, it goes back through R2. There are two directions here. Two directions of the distance vector routing protocol. The direction of route propagation and the direction of data volume, they are exactly opposite. So now after we generate a route on R2's side, then R2 forwards according to the route entry. R2 wants to access 10.1, 0.1.1. We just get the data from 0, find 1, 72.16.1 to 2.1, find R1, then it can be accessed. R1's loopback, zero interface R2, then announces this route. Our database entry, tell it to R3, then in R3's database, show IP EIGRP topology. Then there is such an entry, look at 10.10.1.0. Who told me? R2 192.18.23. Told me I received it from my 0. 1. So I calculate it as a route show. IP route, calculate as a route. then 10.1, 0.1.0. Then I go out from the 0, one interface accessing. R2 can access the 10.1.0.1.0 website. The route, he told I find him in return. So I go to pin 10.10, 1.1. It's connected. Dear students, what needs to be noted is, you see, R2 will not announce my 0, one interface's direct route, 192.168.23.0 to the neighbor of 192.168.23.0. Will not forward my interface's direct route from my interface. But what will I announce? Except for the direct route of 192.168.23.0 in R2's routing database inside R2's database. Except for my direct route of 192.168.23.0. My other? Except for the direct route of the 0. One interface, I can announce all other route entries. Of course, this is from the R3 channel. This will not be announced. 172.16.12.0 and 10.10.11.0 will tell R3. R3 knows 172.16.12.0 network segment. R2 told me. R2 says he is connected to the 12.0 network segment. Then who should R3 find when I want to access the website? Just find R2. Because R2 told me he has. Then I can access 172.1, 6.12.2, and 172.16.12.1. Because R2 told me he is connected to this network segment, and 10.10.1.0. So we found out, after running such an EIGRP, after the distance vector routing protocol, each router, activate the interface you want to run, put the route entries you want to announce into it. Directly connected router is prioritized, right? I want to say R2 suddenly interrupted. We will all announce each router. Let's complete our task. Announce our route entries. Activate our interfaces. Once the neighbors are established, they can automatically complete the exchange of database entries. At this moment, when all the routers in our network have announced all their interfaces, after participating in the operation of our EIGRP, then immediately all routers will have all the route entries in the network. R1 has all, R2 also has all route entries. Then R3 will also have all the website routes in the network. We'll have. This is the benefit and advantage brought by our dynamic routing protocol. Any questions, students? Dear students, it's a bit slow later, no talking aloud. Any questions, students? Can the teacher look at EIGRP? What does that P mean? It's show what IP the EIGRP1 topology. This P means passive. It's in passive mode. If it's active, it means this routing entry is unstable. Of course, we will talk about this later, including the successor route later. What is FD value? It's that feasible, called forward distance. Haven't heard for a long time. It is. As for this thing, we will use it later. No way, I need to hurry up and cultivate the content later, the content in the database. For example, what is our FD? What is AD? What is a successor? What else do we need to learn about feasible? Successor. What does this P mean? What is update query? We will learn all these later. So today what we mainly learned is our EIGRP table, a neighbor table, a topology table, a database table, and our EIGRP packet type. Then we send hello packets to discover neighbors. We'll talk in class for a while. The first function of the hello packet is to discover neighbor routers. We establish a neighbor relationship. But did you notice, after we establish the neighbor relationship, you see between us, R1 is still sending hello packets to R2. R2 is also sending hello packets to this multicast. Even after the neighbor relationship is established, we will always send such a hello packet. Why? So our hello packet has another function called keep alive. We call it keep alive. So by default, the device sends a hello packet every 5 seconds, if it exceeds 3 times the hello time. It's a few seconds if you don't receive the other party's hello packet. It is considered that the other party has a fault. Reset or disconnect the neighbor relationship. Students, our hello packet has another function called keep alive. So if we 2 have already established a neighbor relationship, everyone will know. If we 2 know each other, then after 3 years, 5 years without contact, isn't the relationship faded? So when they establish after the neighbor relationship, they still need to maintain every 5 seconds, just like we get up every morning, say hello between neighbors. So maintain our good friendship. If it exceeds 15 seconds, I can't receive the other side saying hello to me. So I've been sending him messages every day. But the other side has been a week, 2 weeks, 3 weeks. Haven't ignored me. I'm unilaterally giving to the other side. The other side doesn't give me a return. I send him messages unilaterally. He doesn't reply. Does he have a problem? Is there something at home? Is he busy with something? So we are in doubt. Did the other party have a fault? What will we do? Disconnect the neighbor relationship. So once the neighbor relationship is disconnected, so all from the neighbor. The roots learned from him. What are we going to do? Seriously consider whether it can be used. This is our keep alive mechanism. What is our hello packet called? Send a hello packet every 5 seconds. Send a hello packet every 5 seconds. Then, after more than 15 seconds, if no hello packet is received, it is assumed that the neighbor is down. After the neighbor is down, we disconnect the neighbor relationship. Then we check again. Whether this route is reachable. Whether the route can be used, students use this method. We talk about dynamic routing protocols. It can automatically adapt to topology changes in the network. If in our current network, for example, this diagram, one router. 2 routers, 3 routers. For example, this situation, then suppose R1, R2, R3, R4, R5. Suppose R1, we go through R2, R4, and R5. We access behind R5, then 5.5.5.5.5, such a destination address. But if we are at R1, what do we find? We find that R2 has been more than 15 seconds without sending us the EIGRP hello packet. Then we disconnect the neighbor relationship with R2. What do we do automatically? Adapt to topology changes. This link cannot be used. We switch links. Go below to visit 5.5.5.5. This is the automatic adaptation of the dynamic routing protocol to topology changes I can detect, whether our neighbor is normal. If the neighbor fails, we can disconnect, choose another path. Good students, this is the second function of our EIGRP hello packet keep line. If you don't receive the other party's hello packet for a certain time, assume the other party is down. Of course, we can adjust this time. We will talk about it later. How to adjust this time? Then the rest is our EIGRP operation mode. So pay attention. Creating a process must be done. Creating a process does not mean our device running EIGRP. We must activate our interface to run. Only then, in EIGRP, we use the network command line, centralized declaration, declare our interface under the process run EIGRP. Okay, students. This is the simple use of our dynamic routing protocol. That's all for today's content. Any questions? This is a return detection mechanism. We have a simple return mechanism. It's useless. You see, it's sent to yourself. It's a return, port check. It's useless. Don't worry about it. If you want to pay attention to what is useful, it's the CDP that's useful. This thing is still useful. We will talk about what is CDP later. Cisco Discovery Protocol. This is a bit useful. This is useless. Don't worry about it. Any questions from the North teacher? I feel that maybe because I haven't heard about routing in the NA part, I didn't listen to it all. Then maybe the whole logic is not very confident. I want to ask, can I sort it out? Just sort it out. No problem, no problem. You can sort it out. You start first. Not good, you start first, because static routing is very troublesome. So we need some dynamic routing to actively let these, not to manually write, but to let it automatically adapt to all of the routing table to get this. So we need this dynamic routing protocol. The first one to talk about is this EIGRP protocol. Then this EIGRP protocol, it needs to establish a neighbor table. Then this EIGRP protocol, it needs to establish a neighbor table, need to establish a neighbor relationship, to be able to exchange data, this and that entry. Then, when establishing a neighbor, need to send a hello first. That is, send to each other every 5 seconds. What is it called after sending? Directly receive the hello packet from each other. Recognize each other. After recognizing each other. That is, I found out you are my neighbor. In this way, equivalent to finding this neighbor. These neighbors, is it directly connected to it? For example, there are many devices in a network. For example, this switch. Then the switch is a network here, 4 routers. Then, for example, a router sends a hello packet to 224.0.0.1. 0. This runs EIGRP. Then our 4 routers all run EIGRP, can all send hello packets. What can it do? Hello packet enters the switch. Switch defaults to flood broadcast multicast. As long as we don't know our destination, MAC address, we default to flooding. That is to say, in terms of hello packets, enter the switch. Can be sent to all other devices. Then our other devices. For example, we write a device R1, R2, R3, R4. Then R1 sends a hello packet. R2 can receive it. Then R2 knows. I have an EIGRP neighbor opposite. There is an R1, R3 received the EIGRP hello packet. I also know. There is an EIGRP neighbor opposite. R1, R4 also received it. Received the hello packet. I know. There is a neighbor opposite R1. Similarly, every router can receive hello packets from the other 3 routers. Then we also send out hello packets. All other 3 devices can receive. That is to say, for such a network, our hello packet, it can only attract in such a range as long as it is in this link, running EIGRP routers. Then we can all establish EIGRP neighbor relationship. That is, only within a network segment can. That's right, because the router defaults to isolate the broadcast group, maintain unicast. Then after R1's hello packet arrives at R2, will not throw it away. We only have this link. Only on our direct link, we can establish a neighbor relationship. Thank you, teacher. Then there is one thing I don't quite understand. That is the 4th type of address. Isn't it used to establish something like a group chat? Then use this thing to equivalent to sharing and synchronizing routing tables. Is this the meaning? What did you just say about the 4th type? Which 4th type that is? There are ABCD 4 types of IP addresses. Then the class is not multicast IP address, multicast address. Then for multicast addresses, each of our dynamic routers has its own multicast address. For example, rep, its multicast address is 224.0.0.9, our EIGRP. Then it is 224.0.0.10, then it is fixed. Is a completely reserved multicast address. Then you only have the interface. Only the interface runs EIGRP. As long as your interface runs EIGRP, it can join 224.0.0.10, this multicast group, then join this multicast group. After my interface runs EIGRP, then it will do 2 things. The first thing is, then I take the interface, can send hello packets to 224.0.0.10. This is the first thing. The second thing, if a device sends a packet to 224.0.0.10, then because of my interface, joined this multicast group. It's like I joined a WeChat group, send messages to this group. Chat, send messages to this multicast address, then I can receive it. These 2 things. Why is there this multicast? I don't quite understand this multicast. What is its meaning? Because just this diagram, because I can be on one side of a router, I only need to send 1 hello packet. Then if there are 2 routers on the other side, 3 routers, right? Then we use multicast. Then my hello packet can be sent to multiple users. They can all receive my hello packet. Then I can use multicast. As long as they run such an OSPF, they can all receive my hello packet. And their hello packets can also let me receive at the same time. Then using multicast can send messages one to many. Send messages one to many. Then the same way around many to one. Everyone sends messages to 24.0.0.10. Then, as long as we are on this content, we use multicast. We can establish at the fastest speed, establish between the two, establish multiple neighbor relationships. Using multicast can establish neighbors the fastest, of course, if we are on this network. For example, I also run EIGRP, for example. Then I run EIGRP, but I only want to build neighbors with you. Only want to build neighbors between the two. Then it can be done. We will talk about it later. Then under default conditions, EIGRP is sent by multicast send hello packets. Later, we will talk about sending unicast send hello packets by unicast. I only build neighbors with you, only send you hello packets. Then you send me hello packets. We two directly build. How is the boundary of this group defined? In this way, that is, if this whole network all join a group, then how to say all can be sent. Why divide network segments? What kind of this declare network segment, this kind of thing, I can directly publish to the group. But your multicast data, it can't be so messy. Can't be so messy. That is to say, you say, why do we still have to divide network segments after multicast? We still have to divide network segments, right? Is this the meaning? That is, if it is already default, that is, use multicast to send hello packets. Then why is he at that time, when declaring what needs to be declared is his own network segment? Declaration is actually to activate the interface Actually, the network segment you declare, you can write big or small, but it's just that because a root was reserved before use network to declare, then at this time, that is, considering you can freely allocate how many interfaces you want to activate. You can freely allocate how many interfaces you want to activate. For instance, consider this situation. Draw a special diagram. If this is router R1, then I now have 4 interfaces. The address of the interface above is 192.168.1.0, 24.1.1. The address of the interface below is 192.168.2.1, 24. Then this interface address is 192.168.4.1, 24. This interface is 192.168. Think of a good one. For example, 8.1-24, 1 is 1248. Through this network command function we have said, the main point is, it is to activate the interface. Let my interface run the dynamic routing protocol. Then, through this network method, I can freely configure how many interfaces I want to activate. For example, I go to network 0.0-22, which interfaces can be activated to run EIGRP. 1 is 1.0, 1 is 2.0, 1 is 4.0, 1 is 8.1, which interface can run EIGRP. Ah, Jeng just asked, if the two ends of our direct connection between two devices, different network end IPs, are not possible. There is a source authentication. We will talk about it later. Conditions for establishing an EIGRP area. If you two want to be neighbors, at least what should you two do? You can visit each other. If you close the door, you can't visit me, you can't visit him, he can't visit him either. Establishing an EIGRP area has conditions. You must have source authentication. At least we should be able to visit each other. You can come to my house, I can go to your house if you can't even come to my house. How can you talk about establishing a good neighbor relationship? So, on a link, it must be a host address in the same network segment. You can establish it EIGRP, neighbor relationship. It's not possible if it's not a website. We will talk about the conditions for establishing an EIGRP area later. Your direct connection must be available. That's why we say teacher. Before you do the experiment, before establishing an EIGRP neighbor relationship, before doing EIGRP, you have to ping a direct connection first, because EIGRP has a condition. Then you must have source authentication. Your previous direct connection must be available. Only then can you establish a neighbor relationship. Back to the previous question, we can use the network command line to configure by ourselves which interface addresses I activate to run activate, which interfaces to run EIGRP. For example, network is 192.168.0.0. 22 1100 000 10 10 1000 000 000000000000000. 22. Up to here, I type. We can freely configure. For example, -22. The first 22 bits are fixed. Then, in such a website, which hosts does it include? It includes 192.168. The rest are host bits, first from 0.0 to 192.168.3.2.5.5. Then if I use this scheme to declare, then only 1.1-2.42.1-2.4 can be matched. Then only these two interfaces can run EIGRP. Come again. If I change the network segment again, change the range, adjust a bit. Adjust to -21. All right, -21 network segment. Then now host address. All the bits behind are host bits. We include the host address from 192.168. All are 0 in this case. It's from 0.0 to 192.168. All are 14.2, 1177.255. So this is our 192.168.0.0e21. We go to network like this. So which host addresses will it include? 1.1, 1.2.1, 1.4.1. So these three interfaces match to run our EIGRP. It can be even larger. We can hit it through the network command. Its main function is just one. That is to activate the interface. Can be deployed through the network segment. Activate the interface. I want to run EIGRP. According to your own experimental environment, adjust according to your work environment. Of course, the most accurate, the safest. I only want my 8.1 interface to run EIGRP. Then why should I? Network 192.168. 8.1. And then -32. I'll just go like this. 0.0.0.0 precise match. Only this address must match. Only it runs EIGRP. So in our work, we might use precise matching more. Any more questions, speak. Teacher, in terms of switches, it's broadcast, it can flood spanning tree. Because it will, it's not just the directly connected ones that will pass that MAC address. The unconnected ones also pass the MAC address, so it will be a mess. The switch's spanning tree is to prevent loops. It's to prevent loops. It comes with a switch. Default for broadcast packets and multicast packets, as long as the destination MAC address. In my MAC address table, I can't find the associated interface. I will flood. Why do we need a spanning tree? It's to prevent loops, for example. We have two links between two switches. So suppose host A, host B. A sends data to let us enter the switch. Suppose it's a broadcast packet, ARP. So what will it do when it enters the switch? Flood, broadcast, multicast, unknown unicast. We can send it out from above, so both packets can be sent to B. So here's the problem. If B receives a broadcast packet from one interface, what to do? Destination, MAC address, broadcast, what to do with flooding? Broadcast, multicast, unknown, unicast. What to do besides this interface? Flood it out too. Except for the interface where we receive this broadcast packet, flood, from other interfaces, I throw it back. After I threw it back to our switch, destination MAC address, broadcast, I flood it back. Then B receives the destination, MAC address, broadcast, flood it back. Then throw it back again. So this packet will continue to flood in it. Keep going around in circles. Looping, this is also a loop. So what does the switch do? We need to eliminate loops. So how does the STP spanning tree protocol work? So I'm in the network, find a point where a loop might occur, I block this port. Logically, in this way, data traffic goes over and flood over, but the port on the other side is blocked. It can't send, nor can it touch any data traffic. This is not used here. The bottom doesn't go, then send it up. What does B do? When it receives data traffic is the hello packet, a prerequisite for EIGRP. The hello packet is a prerequisite for EIGRP to establish neighbors. So what is it like? Let me tell you how to establish EIGRP neighbors. First of all, as long as the hello packet sent by the neighbor is received, this interface of mine is running EIGRP. I joined the multicast group 0, 0.1, 0. As long as the neighbor's hello packet is received, I can establish a neighbor relationship. What do I mean? It means my neighbor comes to visit me. Then I think he is my neighbor. I unilaterally acknowledge him as my neighbor. For example, if R1 receives R2's hello packet, I unilaterally consider R2 as my neighbor. At this time, R2 doesn't know yet. I don't think R1 is my neighbor yet, because I haven't received the hello packet. Only when R1 also sends a hello packet, R2 receives R1's hello packet. Students in EIGRP. As long as you receive the hello packet, I think he is my neighbor. As long as you receive the hello packet. And then check the message inside. I think he is my neighbor. Only when both sides think the other party is my neighbor, they can normally transfer our database entries. Any other questions? If you have any questions, think about it. We try to ask all the questions. Let's finish the class, because today's content must be basic. Understand it clearly. Any other questions? The question I asked the teacher, it's 1.1 and 1.2. A 24-bit, a 23-bit. They should all belong to different websites, right? A2423. Let me draw it for you. For example, a router, 2 routers. This is R1. This is R2R1's address is 192.168.1.1. 24. Then this is R2. His address is 192.168.1.2. 23. Let's take a look. The first 24 bits are network bits. Then our R1. His interface address, the first 2 bits are network bits, the rest are host bits. We belong to 192.168.1.0. 24, no problem. R2 minus 23. R110000010101001000. What he wrote here, wrote. 2 casually, 0000001.0000010, the first 23 bits. Here, the first 23 bits are network bits. The rest from 1 onwards are host bits. So logical and 000000000. We have crossed NA. The simplest way. Copy the position of 1 directly. 1100 000 10 10 1000 000000000. Write the position corresponding to 0 as 0. Then we belong to the network segment 192.168.0.0e. 23. The first 23 bits are network bits. The rest are host bits. The host bit contains the host address 192.168.0.0. 192.168.1255. This is what our R2 contains. The host address is contained in the network segment. It belongs to R1. I belong to 192.168. I think the host addresses contained in this network segment start from 1.0. I take all addresses to 192.168. 1255. Then you say R1, we recognize 1.0 to 1.255 R2. We recognize 0.0 to 1.255. Can they access each other? Can access it. Although they are different network segments, but they can access each other. We mentioned it before, the conditions for EIGRP neighbors are actually very simple. They can visit each other, they can ping each other, then you can establish an EIGRP neighbor relationship. At first glance, our 2 belong to different network segments. 1 belongs to -23. One belongs to minus 24, but they can access each other. Then you can establish an EIGRP neighbor relationship. GAU-G. Any questions, classmates? Any questions? It's okay. If you have questions about this place, you can ask directly on the spot. You can directly say where you are still confused. In fact, it's nothing more than establishing neighbors between them. Then pass on the routing entry feature. Its difficulty is not particularly great. EIGRP can be considered a relatively, how to say it. Consider it as an entry-level protocol, because the later OSPF and BGP are relatively more complex. But if EIGRP is a very easy to lay the foundation such a protocol. If you understand the work of EIGRP, then later, if you listen to OSPF or BGP, you will find it very handy. This is what I'm telling you, right? If you understand the working method of EIGRP later, you will find it very easy to learn OSPF and BGP. Continue with EIGRP the day after tomorrow. Continue with EIGRP the day after tomorrow. Okay, any questions, classmates? If you have any questions, you can ask again. Our EIGRP topic will probably last for 5 to 6 days. Any questions, classmates? If there are no questions, we'll stop here for today. Okay, up to here. Dismiss, classmates. Bye, we'll stop here for today.